Numerical differentiation using the FFT. So there's a property of Fourier transforms that says if we have a function and we are calculating the derivative of it, the 8th order derivative, so that could be a first order, second order, third order derivative, the Fourier transform of that derivative is the Fourier transform of the original function without the derivative multiplied by a constant, and it's just j times omega to the a power, where a is the order of the derivative. So that's a Fourier transform. We would like to use discrete Fourier transform, or the FFT, and there's a similar property. So the DFT of a sampled function, and we're taking the derivative of that to the a power, is simply the DFT of that function times jk to the a power. So here's the code for doing that. Let's say we wanted to calculate a second order derivative. First, we'll calculate this array k. And so these are sometimes called spatial frequencies, momentum vectors, various other things. So we'll create an array that goes from negative some number up to positive some number. And we would like symmetry here, so let's keep n odd. And then we multiply that by 2 pi over L, and that gives us our spatial frequency. We will then FFT our function. So we FFT the function and then FFT shift so that we put the 0 order term in the middle of that array, f. And that'll be consistent now with our spatial frequencies. So at this point, we do our point-by-point multiplication of our DFT data, and then our I times k dot to the a power. The dot to the a power because we're taking the exponent of each of these individually. We're not doing any kind of matrix row vector stuff. So we now have sort of a modified DFT array of data, so that's no longer the pure DFT. And so we will inverse FFT and inverse FFT shift that, and that brings us and calculates our derivative that we can plot. And so we can then compare our derivative to the original function and learn a lot. One consequence of using the FFT to calculate derivatives is at the edges of your function, it assumes a periodic boundary. And so if the edges of your arrays from the left to the right are grossly mismatched, you're going to see some kind of impulse function when it's calculating the derivative at the edges. So here's what that looks like. Let's say we have a cosine function. We will FFT that. We will multiply it by this other array. And when we multiply all that, here's what that looks like. I'm not sure what we learned from that, but that's what that looks like. This is what we inverse DFT. And when that's done, we get the derivative of our original function. And now we're looking at since that's a second order derivative, we're looking now at a negative cosine x. Now this is really cool. We've just come up with something that lets us calculate fractional derivatives. A does not have to be an integer here. In fact, it could be anything. We can calculate a half derivative, a 2/3 derivative, a 0.837 derivative. And so what I've done is I provided here some MATLAB code to take you through a sequence of derivatives. And here's what that looks like. This would be the original function. This is its half derivative. Here's the derivative of that function, the first order derivative. Down here is our second order derivative, and here's a 1.5 order derivative. And we really could calculate anything in between. Let's look briefly at how the MATLAB function works. So we'll choose 101 points, that's an odd number. We will create our array x from which we calculate our exponential centered at 0. Then we'll calculate an array of derivative orders. So I want the 0 order derivative, that's the original function, the half, the 1, the 1.5, and the 2. Maybe you want more, in which case you can change this, but I'm creating an array that goes 0, 0.5, 1, 1.5, and 2 because that's what I want to display. And then I'll just get the length of that to see how many I'm displaying. Rather than just hard code that to a 5, now I could just change this array and it will automatically adjust and display a different number of derivatives here. Okay, now we actually want to calculate and show these. So I'll first calculate L. That's essentially the period. It's the distance from the left to the right, so I'm kind of interpreting that as a period. Then I will set up a loop for each fractional derivative I want to calculate. For each of those, I need an array of my spatial frequencies. So in the square brackets is an array that's going from minus n over 2 to positive n over 2. Then we do an FFT shift and an FFT. So first, it's really the FFT, then the FFT shift that centers the FFT because our spatial frequencies are centered. Now we multiply it by ik to the a. We're doing a point-by-point multiplication. So this is no longer the DFT. It's a scaled version. And we will inverse FFT shift that, inverse FFT. And then I also like to take the real part because sometimes there's some small imaginary noise left over. So I just get rid of that. And now I have the derivative, which of course I can then plot. And when I do that, I see my sequence of fractional derivatives. Really simple code.